things. Obviously, the homework is due today. The project part 2 is released, and so Sushovan is here. If you see Sushovan, it cannot be good news. So he's going to talk to you about a little about part 2 of the project, and then after that, I will start the lecture. And then, as he is doing his part, I'll try and see if I can distribute the homeworks. If not, at the end of the class.
So, in project part 2, you are required to do two things. One is authorities and hubs, the other is PageRank. So, for both of these, you need to know the link structure of the pages that you are indexed. Right? You need to know which page points to what other page. So, what we have done is we have given you 3 files. One is linkanalysis.java, and then it depends on 2 files. One is int citations.txt and int links.txt. These files essentially describe the link structure of the pages that are in your index. So if you open int links.txt, you will find document numbers listed in there, and then an arrow pointing to what other document numbers it points to. So for example, document 1, then an arrow, 3, 4, 5, etc. Now you don't have to worry about that because linkanalysis.java does the hard work of reading through this file and giving you a list of document numbers that each document points to and is pointed from. Okay? So what you have to do is download the files and run it. There's a small demo program in there that will give you the documents that point to and point from document number 3. Just run that and see if it works for you. Okay? So in order to get every document that points to document number 1, 2, 3, you call this function. You say linkanalysis.get citations 1, 2, 3, 4. That will give you an array of integers. Those are the document numbers that point to 1, 2, 3, 4. Okay? And if you want to see what documents 1, 2, 3, 4 points to, then you can call linkanalysis.getLinks 1, 2, 3, 4. That will give you all the document numbers that 1, 2, 3, 4 points to. Okay? So you should already know how to do authorities hubs computation, but a quick refresher. First, from your Lucene index, using your project part 1 code, you find a set of results. So you use TF-IDF code that you developed already in part 1, and what you get is called the root set. They are the original set of answers for your query. You take that root set and you use this linkanalysis.java file to grow it into a set of pages called the base set. Alright? So for every document that is in your root set, you look at all the documents that point to it and all the documents that it points to. And that entire group of documents becomes your base set. On this base set of pages, you perform the authorities and hubs computation, and that will give you your final results. Is that clear? So you should already know how to do this iteration process. You find the adjacency matrix, and then you say A transpose A, and then you iterate over it. That should give you authorities and hubs. For PageRank, what you will do is the following. You pre-compute a PageRank value for every page, because computing PageRank is a very time-consuming task, so you should pre-compute it. And then you take W times the PageRank value plus 1 minus W times the similarity score that you found in phase 1. Okay? So the question is, how do you pre-compute PageRank? As I'm sure you already know, you have the adjacency matrix M, and then you add to it the adjustment for sync pages, and then you add to it the reset matrix. Then you get the adjusted link matrix called M star. And then if you do this many number of times until you converge, until your PageRank no longer changes, what the final R that you get is your final PageRank values. And what you should do is you should compute this R and pre-compute it and keep it in the safe place. You could keep it in a file, you could keep it in memory, that's fine. And then whenever the user gives a query, you look up the PageRank value from the cached value, you add the similarity score to it, and finally you get your final score. So a couple of things you should remember is normalize the PageRank value. because usually the PageRank value is very small. It's distributed over 25,000 pages. So obviously it is small. So you should normalize it so that the PageRank lies between 0 and 1. The smallest PageRank value of your entire index should be 0 after you finish the normalization, and the largest PageRank value of your entire index should be 1 after you normalize it. Only then will you find a noticeable change in your vector similarity scores. Otherwise, you will get the same results every time. To do that, the other thing you should do is, for authorities and hubs, it's okay if you create the entire matrix. It's not too large. But when you try to do the power iteration for PageRank, you will typically run out of memory if you try to keep the entire matrix in memory. So there are multiple ways of doing it. One is you could keep a sparse matrix around. So that's one way of doing it. The other way is you, whenever you need a particular element in that matrix, you call linkanalysis.java and retrieve it. You don't keep the entire, you don't construct the matrix. Whenever you need it, you compute the value using linkanalysis.java. That's another way of doing it. That's about it. For authorities and hubs, you can easily check whether your code is correct or not, because you can create your own version of linkanalysis.java with only 3 nodes and then check whether it gives the right values or not. For PageRank, it's a bit more difficult, but you can do that. So, any questions? Yes?
So, when you analysis about text, the number that we give it is the production ID for the losing index? Or
Yes. Yes.
And if we recompute our index, is it possible to recompute those values also? Be provided for a method for it? Or no?
Yes, it is possible. There is so if you look at the problem statement at the very end of the page, there is an optional section that tells you how to do it. Any other questions?
Thanks. Okay, so if I return your homework to you, I already know your name, so you are not, don't sleep in the class. The rest of you, I'm not completely sure. So, so you can continue sleeping, and then I have to find out who you are. We'll do it in the end of class. But as I said, project part 2 is released, and you got some of the background on that. The midterm would be either next Thursday or the Tuesday after that. I'll let you know which one it is, but I'm just giving you a heads up. Okay, it's not like in some unknown future. It's either next Thursday or the Tuesday after that. But I'll let you know soon. My next class. Then. Okay, so that's where we are. So I am actually going to continue the discussion that we were doing last time. Try to complete the discussion on stability and robustness of PageRank and authorities hubs, and then start talking about actually some of the engineering issues that Sushovan was also talking about. Okay. Before I go there, are there any questions? Yes.
I don't know if this is really important, but on the test, are we going to be responsible to know how to compute SVD? Like do the entire SVD? Well, I know, but I meant like do the entire calculation, because that took a little bit of time.
Well, I mean, I guess I don't want to rule out anything.
Right.
So I think you should know everything, but obviously if it's an in-class test, there's only so much I can reasonably expect people to be able to do in the given amount of time. Although I am very creative in expecting people to be miracle workers. But even I might have trouble in assuming that you would be able to do SVD and LSI and PageRank calculation and then get done. Yeah. I mean, to some extent, I think the homework, get you to do more things than exams can. And yes, you had a question.
I had a question about what's going to be test everything before the test?
I will let you know that. But definitely everything that's got done is going to be on the test. More likely, this week's material will also be on the test. And the class just before that would not be on the test. Okay, and then this week's material, actually, I think there's not going to be a separate homework, so it will still be on the test, but there won't be a separate. Any other questions? Okay, so last class before we left, we were talking about topic-specific PageRank. At least that was my last slide. Is that what we were talking about? Can somebody remind me how we were using reset matrix in topic-specific PageRank? Because my first order of business today is to talk about all creative ways you can use the reset matrix in the PageRank computation. And one of which was with the topic specification. Yes?
Yeah, so in this case, we are actually going to use different reset matrix as per the domain. That's what we discussed.
Yeah, so how does it differ? So for each topic, there is a separate reset matrix. So first of all, you realize that for the topic specific PageRank, if you assume that there are 10 topics, then each page is now going to have 10 different PageRanks. One for sports, one for computer science, one for science, one for entertainment and things like that. Okay, so on each of these PageRanks, the link matrix is the same, essentially. Although I did mention that you can actually also try to reinterpret the link matrix such that the links which are about the sports are given higher weight in the sports topic, and which are about computer science and science are given higher weight in the science topic. Okay, but the paper on topic-specific PageRank that somebody wrote years back, they didn't even try doing that. All they did was they just changed the reset matrix. So the idea is you follow the exact same link matrix, and then but with the probability 1 minus c. Yeah, when you get bored, you are not going to go to all pages with the same uniform probability. If you are in the sports topic, then you are likely to go to the sports pages with higher probability than non-sports pages. Okay, so they're going to start with 10 different reset matrices and compute 10 different PageRanks. So that's the way topic-specific PageRank works. Okay, are there any questions on that? Okay, so the idea is that in some sense, what differentiates this from normal PageRank is what do you do when you're bored? And when you're bored, if you are a sports fan, you will go to sports pages. If you're a science fan, you'll go to science pages. Okay, and if your query is a science query, then probably it makes sense to think in terms of the science rank rather than the sports rank. Okay, so that was the idea. What I want to say is that actually there are a whole bunch of ways in which you can co-opt the reset distribution. Okay, so reset distribution was it was thrown in mostly to make the underlying Markov chain irreducible. That's all. That was the real reason. Okay, but it's not necessary that, so all we need is the reset distribution make sure that every page is reachable from every other page. Okay, so as long as there are no zero entries in the reset matrix, you're guaranteed that this will happen. Do you see that? As long as there are no zero entries, you're guaranteed it will happen. You don't necessarily have to spread the probability mass uniformly. You know, what we wound up doing originally was we also spread the probability mass uniformly. You said 1 over n, 1 over n, 1 over n, right? Everywhere. Okay? None of these are zeros, so obviously it's going to make sure that the underlying Markov chain would be irreducible. That means it will be connected. Each page will be connected. But nobody stops you from saying these pages, these 3 pages will get 20 over n, and the rest will get n minus 20 over n. As long as they add up to 1, you're fine. Right? I mean, that's the whole point of probability distribution. I mean, if you have a probability distribution, the real question is, the total mass under the probability distribution is the same. It's just how do you put, which are more likely, which are less likely. You can keep changing. Okay, so in topic specific, we basically said for the sports rank, we'll put higher weight on the sports pages and lower weight on the non-sports pages. Now, you have to ask me, if you are actually paying attention, how did you know what are the sports pages? And the assumption there was that you went to this directory and found some of the important sports pages. And you just gave them a big boost at the expense of the other guys. So some of the other sports pages will also be in the non-descriptive category. Okay, but a few sports pages will get like maybe 20 over n of the probability mass. And let's say that you got 3 sports pages, you might give just with those 3 of them, you might give 100 over n of the probability mass, and the rest of them, basically share the n minus 100 over n. That's the basic idea. Okay. Now the interesting thing is that you can change this. You can use this kind of an idea to do all sorts of different variations. For example, before I get here, let me talk about recency rank. One problem in using pages on the web, especially if you are doing importance measures based on link structure alone, right? Then if you are a new page, you don't have any links. You may be important, but nobody is yet pointing to you. You just came into being. How can you have people pointing to you? How can you have pages pointing to you? And so new pages will never ever come up high enough in terms of PageRank, right? So you need some affirmative action for them. Okay, how do you do the affirmative action for the new pages? Again, recency. In the reset matrix, you give a little higher weight to recent pages. So recent pages as a group will share more of the probability mass than is really supposed to be shared by them, if everything is equal. And the older pages, they essentially share the rest of the probability mass. Okay, if you do this, this is a new paper now. It actually was an old, it was a new paper some years back, 3 years back. Okay, all this guy did was wrote a whole entire page explaining that after all, we all agree that recent pages are given, being given a short shrift, and we need to do some affirmative action. How do we do affirmative action? We can give higher weight to the recent pages. It's not too hard, you can tell when the page is created, and based on that, you can give higher weight to them. And once you do that, basically, it just ever so slightly biases the page rank so that, you get a little affirmative boost for the recent pages. That's recency rank. Okay. I can also talk about trust rank, which is, in some sense, actually, the interesting point, of course, is PageRank is supposed to be, all importance measures are supposed to be able to try and find out for you the trustworthy pages. Now, of course, the problem with trustworthiness is different people have different notions of trustworthiness. Suppose there's a war going on between 2 cultures or 2 countries, right? One country will think certain news sites are the trustworthy news sources. Another country will think certain other news sources are the trustworthy news sources. Okay? And so, I'm not, when you're actually looking at, when somebody from the country 1 wants to look for something, okay, they probably want the sources that they trust more. Do you see what I'm saying? Okay, so the question then is, can we actually differentiate sources based on their trustworthiness? And actually, the most extreme case for that is user-specific PageRank. Everybody has their own trustworthy pages. So really, there should be a separate reset matrix for everybody. Okay, so you'll have a personal PageRank, and you deserve it really. You should send a mail to the search engine saying, I should have my own PageRank, and you should use that PageRank to give me my results. And that might, for example, take into account what pages you tend to go to when you're bored, what pages you find trustworthy, for example. Okay, but obviously that way there will be like 6 billion PageRanks. So what I might do instead is essentially the trust rank. The idea is you try to differentiate pages again in terms of their level of trustworthiness. Now it looks like PageRank is supposed to do that already. There is an interesting way in which you can basically use this idea that not all links are created equal. So if there are certain trustworthy pages that everybody agrees, for example, New York Times or Washington Times or something, although there are no two people who agree that both New York Times and Washington Times are trustworthy at the same time, if you know what I mean. But if you found the trustworthy sources, then essentially you start from there, and if there is a link from the trustworthy source to you, then you are also sort of trustworthy. So you can talk of a transitive closure of trustworthiness and use that to figure out trustworthiness of pages, and then make the reset matrix be proportional to the trustworthiness, and then compute the page rank. Okay, and so all the work that you did was first computed the trustworthiness of the page, and then you just made the reset matrix be proportional, reset matrix entry to be proportional to the trust, and then you used it in the page rank.
So somehow we are using authorities hubs and incorporating it into.
It's not exactly.
But it looks like that.
It's sort of. I mean, again, I think it's a paper worth reading. All these ideas, there are papers in the readings list. They are probably indented. That means you don't have to read it to just pass this course. But if you want to find out exactly how they did it, there is a paper on trust frameworks. Okay. So, but the interesting thing from this class point of view is you are essentially just using, even if you figured out what are trustworthy and less trustworthy pages, there is a way in which you can put that into the soup. You just change the reset matrix. So reset matrix is, has lots and lots of interesting uses. That's what I want you to think about. It just basically came into being because we wanted to make sure that the Markov chain is irreducible. But then you started finding interesting uses. Okay, so if you want to find some new type of page rank, the first thing you want to think about is how do I change the reset matrix such that it would have the right behavior. Okay, so I tend to think of trust rank and user specific page rank as one level, and a topic specific page rank. And so topic specific, remember when we mentioned topic specific page rank, I mentioned that you can have page rank, which gives one level of importance for every page, and then query specific importance is different from global importance. And if you do query specific importance, then you compute page rank after the query, after you actually run the similarity computations for the query, and then get the pages, and then do page rank on them. Okay, that unfortunately takes time after the query has been presented. Okay, so we went with topic specific page rank. And similarly, user specific page rank, to many users, you might be able to get by with, what are the, so what are the sites that users find trustworthy, general user populations find trustworthy, and give them higher probability when, at the reset matrix. Okay? So that's just keep in mind this source of good ideas for changing these importance measures. So the next thing that I want to do is stability and disruption, stability with respect to disruption and attacks for your importance measure. So the interesting thing is query you pick, and whether or not the query is similar to the file basically must have content that makes that similar to the query. Okay. This is a notion of importance of a page measure, importance of a page that you are computing separately. And so the question is, how robust is it? Is it going to change too easily? Okay, and there are like two different questions we want to ask, and we want to look at both of them. Okay, first is, if there is a random disruption to the link structure of the web, would the importance measure change too drastically? And random disruptions are happening every day. Like suddenly I remove a page from the web, okay, which basically means if there was a page that was pointing to this page and this page was pointing to this page, now this is gone, so this link is gone. Right? And it's happening every day. So if for every little few links that disappear, if importance measure changes completely, then it's not a particularly good importance measure. Okay, and the second issue really is adversarial aspect of the information retrieval on web. Okay, to the extent the pages, if page importance matters, and it matters, you will realize that you would like your page to come high up, and especially if you are commercial, if you're a company, then you want your page to come high compared to your competitor, and you're willing to pay, you're willing to do whatever it takes to get on. So the question then is, how easy is it to game the system? Okay, those are the two questions I want to talk about. Okay, so let's start with this simple example, which is basically, actually, turns out it's connected to the part of the homework that you didn't have to do because I didn't do it last class. Which is basically, I have just this link structure. I have a 1, 2, 3 are pointing to 4 and 5, 6 and 7 are pointing to 8. Okay, suppose I do authorities and hubs on this. Who are the big authorities here? 4. And, okay, tell me all the good authority pages. 4, 8. 4, 5, and 8. And the good hub pages are 1, 2, 3, 6, and 7. Right? That's what your intuition says. Right? If you were to run authorities hubs on this, okay, so intuitively this is what you would think. This is what you said. If you were to do authorities and hubs, you run it yourself. Okay, actually you can go home and run it. In fact, next page I tell you, you don't need to run it. You can reason it out yourself. If you run the authorities hubs, after the power iteration, you will find that 4 and 5 keep the entire authority, 8 dies. 8 has no authority. Okay, and 1, because 4 and 5 are the only authorities, then 1, 2, and 3 are the only hubs, because this guy is pointing to a loser page. Do you see what I'm saying? Okay, now this is a counterintuitive point. Okay, now the first thing you want to ask yourself is, am I making this up? Can I actually reason this out other than just depending on MATLAB? And it turns out, in fact, this can be thought of as a tyranny of majority. All that matters is that if the number of entities in this cluster is 1 more than the number of entities in this cluster, that's enough. If there are a million pages here and if there are a million pages here and 1,000,001 pages here, then this guy gets all the authority and hub, and this guy gets none. Okay? And why is this? It turns out that you can actually reason this out. So imagine that if you take the same kind of a structure but a slightly simplified one, here there are M guys are pointing to P, and P1 to PM are pointing to P, Q1 to Qn are pointing to Q. Okay, so now if you were to do authorities hubs iterations, let's do it a couple of steps. So if you assume that we all started with 1, 1, 1 for everything, okay, authorities are 1, hubs are 1 for every page. Okay, after the first iteration, the authority of the page P would be M guys, right? And the authorities for page Q would be N. So this is M, this is N, and then you need to normalize it because it's an Mn vector. If you normalize it, you will get M by square root of M squared plus N squared and N by square root of M squared plus N squared. Agree? Okay? So now what you do, you need to talk about the hubness. The hubness basically would just be for H1 of the PIs would be M by square root of M squared plus N squared, and for this would be N by square root of M squared plus N squared. Okay, now the next level what happens is the authority would now be in terms of the hub guys. So the second iteration, the authority of page P would be M square, because there are M guys pointing, each of them have M authority, M hubness. So M square, and of course it would be divided by M power 4 plus M power 4. And similarly for Q, it would be N squared by M power 4 plus M power 4. Okay, so all I care about is the authority of Q divided by authority of P, which will cancel these guys out. And so it will just be N by M squared. So here the authority of P by authority of Q was M by N. Here it's M by N squared. Okay, so it looks as if there's only one mathematical reality in this course, which is if ever you exponentiate a number less than 1, it becomes 0. That comes to your rescue again, because if in fact n is less than m, or m is greater than n, then n by m is less than 1. So once it's less than 1, if you exponentiate it, it becomes 0. So by the fixed point, as the number of iterations tends to infinity, it has to be the case that the authority of Q by authority of P is 0. That means Q has 0 authority relative to P. Okay. So now what happened in this case is this computation is doing what it is supposed to be doing. There is nothing that was wrong in what is being done. You just like this computation in some small area, and you try to call them authorities and hubs. But in some other examples, your intuitions and what this computation is doing are just divergent. Do you see what I'm saying? Okay, so first of all, that's an interesting point to realize that authorities hubs that you kind of, the homework part 2 essentially was saying if you were to do 100 iterations, what happens? And what happens is the big cluster gets all the authority and hub, and the small cluster just dies out. Okay, now before, so now you might be thinking this is bad, obviously, but then, if you have lemons, let's say you can make lemonade, right? Let me go there and show you this first. If in fact there is, if the big cluster gets all the authority and hubness, and the small cluster just dies out, and you are trying to, suppose you have a situation in your link matrix where there are disconnected clusters, and you want to find out, all the clusters one by one. You can use this method. Okay, you do authorities hubs first, and then the biggest cluster will get all the authority and hubness. So then, basically at the end of the computation, take out all the nodes that have non-zero authorities and hubs. That would be cluster 1. Remove it from the link, basically the graph. Then you run the authorities hubs and the remaining disconnected components. You'll get the second biggest component. Then you run it on the third biggest one. Then once again you get the third biggest one. So in fact, this is a reasonable way of computing disconnected components on the web, on a link matrix. Do you see what I'm saying? Okay, and then in fact, this sometimes might actually give you this, again, continuing the lemonade making, this is very interesting actually. This idea that this problem exists for authorities and hubs was pointed out also in Kleinberg's paper. If you're writing a JSCM paper, you don't want to say that it's a bug. So you want to make it a feature. Okay? So the feature, the way of looking at it as a feature is that actually it can be used to get one community after other community out. And furthermore, sometimes if I were to ask, this example shows you how many years these slides are being shown. Because if I were to use the query house, okay, it turns out that there can be one big component, okay, which is basically US House of Representatives. And then there is a smaller component which might be, in this case, about buying houses, for example. And the third component could be Dr. House on Fox network. Okay, and so the idea was he was sort of saying that this way you can, if you don't have anything else to do, you basically run the authorities hubs. So when you did house, you got a whole bunch of results. You got a whole bunch of results, right? Let's say you took the top 200 or something, and then some of which are about the US House of Representatives, some of which are about buying houses, some of which are about House the show. Okay, and you can figure out that there are these three different clusters by essentially first running the authorities hubs on the whole set and removing the first cluster, rerunning it, removing the second cluster, rerunning it. I'm not saying this is the most efficient way, but it does give you those three notions of the query house. Yeah.
Are you suggesting that there is a connection between link closure and topic closure?
There could be. Presumably, the idea is that the pages which are about Congress-oriented stuff will be pointing to Congress rather than building houses. Although, after the housing bubble burst, then there were things which were talking about the House members did stop the housing bubble. There you got both being used at the same time. But anyway, so it's like the links. It's actually a very good question, which is if you can make clusters based on link structure versus based on the content structure, how would those clusters differ? We'll talk about it a little later again. But authorities hubs is a way of computing clusters. When it fails, it can compute clusters for you. Okay. Now, up to that kind of looks like I was able to make a bug into a feature, right? The real problem is this. Suppose you are living happily like this, right? And so there are like million pages here and 1,001 pages here. And then some random page was created overnight. We just happened to sort of put one link to a page here, one link to a page here. Okay? The moment you did that, they have become connected now. Okay? If they get connected, now notice that this, I would say, is a random change rather than a very carefully premeditated change, because there are, millions of ways of basically taking a page from here and a page from here and, putting a link, right? So pretty much with a high chance this could have happened overnight. And the next day morning, if you were to run authorities hubs, then all of a sudden, actually 4, 5, and 8 will all be authorities. Okay, and 1, 2, 3, and 6, 7 will all be hubs. Now notice that I'm actually turning my intuition around. Originally I wanted 4, 5, and 8 to all be authorities. You convinced me that you can't do that. You will only get 4, 5 to be authorities, 8 won't have any authority list. Fine, I'll live with that. But don't keep changing your mind every night. You see what I'm saying? I'm mad about your flip-flopping, not about the fact that you have no clue what is importance, because I don't have any clue either as to what importance is. Okay, so this is really a much bigger indictment. If importance changes because of a small random link being connected, then you are not, it's not a robust measure. Okay, so this is sort of a bad news from the stability point of view, and of course, if you are paying attention, there are easy ways of fixing this. Authorities hubs happened not to fix this because authorities hubs didn't think of it from the point of view of Markov chains. Okay, and if you thought about Markov chains, then you would have thought about irreducibility, and you would have put weak links between every page. And you could do that here too. You could essentially have said every page has links to other pages, but also has weak links to every other page. And so then the adjacency matrix won't be just ones and zeros, it will be 0.9 and 0.001 sort of matrix. Then if you do primary eigenvector for that, okay, then it won't have this problem, because in some sense, by putting weak links, you are already inoculated about, from this kind of a problem. You see what I'm saying? You already inoculated yourself from one random link connecting to clusters, because you said everything is connected anyway at different levels of different degrees. Okay, so the interesting thing is that it gives you an idea of what would happen if you, from the authorities hubs point of view, if you don't do weak links. Standard authorities hubs doesn't do weak links, but there's no reason why you should. Okay, and if you don't, this is the problem you get. And in fact, there is some study that has been, in fact, even though I mostly told you this whole thing as in an anecdotal way, there are papers which actually looked at the stability of the PageRank method and authorities hubs method. Okay, in deciding, in this particular case, this guy Andrew Lang essentially took a whole bunch of machine learning papers, looked at their citation structure. Papers, refer to each other. So those are the links. Okay? So using that links, he tried to figure out mirror on the wall, which is the most important machine learning paper of them all. Okay? And then he computed that using PageRank as well as authorities hubs. And then he went ahead and randomly removed certain percentage of citations. Just removed certain percentage of citations from across all the papers, randomly. And then recomputed the importance. The question is, whose importance changed? It's not who knows what is important, whether PageRank knows whether something is a good machine learning paper, or authorities hubs knows whether something is a good machine learning paper, but which of them are changing their mind too fast for small random changes. Okay, and it turns out that this paper basically points out that authorities hubs changes its mind too fast, and so it's not stable. So in fact, he was the guy who actually pointed this out. Now, obviously, I'm telling this to you as a textbook material, but this was one of the first times it was pointed out. And what's interesting is that he actually came up with a different solution for handling this problem with authorities hubs. Okay, the one easy way, as I said, if you want to stick to authorities hubs, you can put weak links in the adjacency matrix, and that should take care of this problem. Okay, a different way is, it's kind of interesting technically, but that's the one that Andrew Lang actually pointed out. Nobody actually uses it, but it's a neat point, which is that why exactly do authorities hubs the importance measure change? When does it change significantly? You know that it does change when there are disconnected components, and they suddenly get connected. But in general, in a more general way of looking at it, when do these things change? Okay, when do these things change? The other interesting point is eigengap that we kept talking about in this class. What's eigengap? The difference between the primary and secondary eigenvectors. Okay, his point is if the underlying matrix has low eigengap, that means the lambda 1 and lambda 2 are close, then in essence it looks obviously like a circle, because only circle has, at least in one projection, in the projection that is perpendicular to, in the projection that contains both the primary and secondary eigenvector, what you get is a circle. Right? That's the only time when you have eigenvectors being very close to each other. Whereas here, this eigenvector is much smaller than this one, so eigengap is much higher. And it also means that it's actually more ellipsoidal. Well, circle is an ellipse too, but it's not a good ellipse. Okay. Now the interesting thing is that as link structure changes, then essentially this circle becomes slightly different ellipse. Similarly, this ellipse becomes a slightly different ellipse. For you, it's not a big deal. But from the access point of view, it's a huge deal, because once this circle, you almost don't see any difference between the original circle and this very close to that circle ellipse. But this ellipse has completely different eigenvectors. And you are putting your entire measures of importance on the direction of the eigenvectors. The sizes haven't changed, they're almost same. This becomes slightly smaller than this, but man, their directions completely change. And if the direction changes, the importance measure changes completely. Do you see what I'm saying? Whereas here it doesn't change as much. And so the importance measure doesn't change as much. So his argument was that if you were to start with a matrix, use eigengap, if the link matrix were to be such that the original eigengap was close to 0, then you are dead. If it is very large, then you are not likely to have any problems. Okay, that's a very good explanation, first of all. Okay. Once you make that explanation, then the other idea he said was, well, all you wanted is a vector, right? That's all you wanted. So that you can then use that vector as measures of importance. Okay, so you wanted to take this vector, which is the primary eigenvector, and that just seems to be changing all over the place. Okay, but what's interesting is in both these cases, if you consider the plane in which those vectors fall, that plane is the same. So if you were to take the cross product, how many of you remember the cross product? Okay, cross product of vectors basically, two vectors is another vector that's perpendicular to this. Right? Okay, so if you take the cross product doesn't change at all. It changes very little. These guys can keep going round and round in circles, but their cross product is this. Do you see what I'm saying? Okay, so he argued, why don't we use the cross product as the importance measure? Now, when I started this discussion, I must have sounded strange when I said it almost doesn't matter how you define importance. What matters is that it's stable. And you're thinking, how could you do that? People who define importance know something about importance. Nobody knows what is important. Okay? What does matter is stability and the ability of the system not to be gamed too easy. Okay, so in this particular case, he just took the primary and the secondary eigenvectors, took their cross product, and uses that as the importance measure, and shows once that is done, A, first of all, it's pretty stable, irrespective of the eigengap, and B is just as good as PageRank. And who is to say whether this paper is the most important, this paper is the most important, when both of them are really quite important anyway? You see what I'm saying? Okay, so that's a very nice idea. Again, that paper is also there. You can read it up. To understand it, you probably need to know a little more on the linear algebra side. But I brought this up because it gives you there are two different ways of fixing authority subs so that it becomes more stable. Okay, one is very simple, which is this weak links. The other is actually kind of counterintuitive, but more interesting. But you may not use it ever, but understanding that works tells you what happens in importance computation. Essentially, take some reasonable features into consideration and be stable. That's what matters. Okay? And once you stick to it, then people will try to game your system. US News and World Report, as I said, if they started saying, inner city high schools were the best universities, people would have said, obviously, you have something wrong with your, ranking. But as long as they get the, remember the end of Casablanca where this guy says, round up twice the usual number of suspects, right? So if you round up the usual suspects and put them in the top few places, and every year just change their order so that people will buy the new version of the US News and World Report's rankings. Okay, by the way, so US News and World Report, it's interesting, sells its rankings. Okay, they'll only show the top 10 rankings. That's what will get published in New York Times and everything. And then if you want to figure out whether you are 154 or 155 in their ranking, you need to pay $15. Who do you think pays money to US News and World Report to find out the ranking? The people in the top 10 don't care. Right? If US News and World Report said, we have a ranking of top, 10 universities, and we won't tell you what it is unless you pay us $15. That's a useless business model. Nobody will pay for it. Whereas you give the top 10 and then say, if you want to find out your ranking in our ranking, your placement in our ranking, you just have to give $15. And so then you want to tell your friend that you're going to a university which is 154 compared to your loser friend's university which is 155. Right? So you pay $15 to get that information. Okay? You see what I'm saying? So, and then so in essence, really, if it hangs around long enough time, people will try to find out what their rank is and game the system to improve their rank. Okay? Knowing fully well, everybody in the process knows that these rankings don't mean anything, but people will play with it. Okay, so the next part that I want to talk about is robustness against adversarial attacks. So if you are stable and you stick to your word and you say these are the good pages, these are less important pages, then if you are at all, as a search engine, if you are at all successful, then everybody wants to be in the top of your rankings. Okay? What do? To improve your ranking, you have to game the system. Right? For example, I mean, I wouldn't go into very specific details, but US News and World Report, it turns out, one of its features for ranking universities is how big are the classes. Okay? And they decide the bigness as a threshold. 20 and above, big class. 19 and below, small class. You know, people don't come in fractions, so you don't need to worry 19.5. Okay. So the real question then is, if you have small classes, it's a good university. If you have big classes, it's a bad university. Right? This is no. So what do you think? If you are a university president, what do you think you will do? You will have to generate a huge number of classes that are small. Okay? So in lots of places, there are 19 capped classes. And some of you know a course in ASU which is capped at 19. Okay? And because ranking matters, I will find a way to get ahead according to that ranking. Okay? So the same thing in the page importance measures too. If the page importance measure matters so that you will come higher up on the top 10 results and people are likely to click on you and buy stuff from you, you want to get there somehow or other. Now, supposedly the search engine doesn't want to be too easily gamed. So they need to find out some ways of stopping the gameability of the system. Unfortunately, you cannot completely stop the gameability of the system if you are computing one level of importance for across all the queries. If you have a global measure of importance, such as PageRank, which is just computed independent of the queries, that's asking for trouble. Because you can do all sorts of things to somehow improve your importance with respect to that. Now, it would be much better if the search engines computed the importance with respect to the query. Remember the two methods of computing importance. If you did it with respect to the query, it will be much better. But search engines won't do it, because if they do it, you'll get mad at them that it's taking too long to compute the query. So they'll go ahead and compute importances before. Right? And so you have if you want to game the system, you have enough time to game the system. So the question then is, obviously you heard lots of these, so the next few slides are some examples of this, but let's start with some theory. If I have a linked matrix like this, A, B, C, and the only difference here is B and C colluded, and C put a link from B. That's it. Okay, would PageRank change? Clearly, in this case, if you compute, in fact, this is again, I'm giving a large number of examples of PageRank computation, by the way. You might later on yell at me saying you didn't do any homework, any examples in class, but these are all examples. You should be able to reproduce these. So this M star matrix for this would be this, M star matrix for this would be this, and if I were to compute ranks here, not surprisingly, this is actually, this says all of them are equal rank. By the way, notice that this is what we mean by periodic, right? And so there is not supposed to be any stationary distribution. However, you took the periodic distribution and then, so anyway, so in this case, they're all equal, which is basically what your intuition also is. In this case, by just putting this extra link, C and B became richer at the expense of A. What does this mean? If there is a link of pages for the class, and some of you collude and put more pages to each other, more links to each other, then you all become more important than the other people who did not take part in this collusion. Furthermore, if a new student comes and they want to make the page, then this closely colluding group can tell this other student, if you kind of give us like $15 or something, we will put a link from our cluster to you. And then you too shall become important. So first it was just to make yourself important. Next it became a business model. You are actually, getting money from new students who will pay you money to join your cluster. Okay, for some reason I'm going to be, I get this, the picture I get when I think of this is in the winter, if you sort of, you keep putting more and more links, this cluster is highly charged. It has a large amount of importance, okay? And then you touch any page, that page also gets importance. Okay, so for some reason the thing that comes to my mind when I think of that is in the winter, you sort of rub your feet on the carpet, and whenever somebody comes, you touch them on the nose. They get a nice big shot. Okay, so that's what you are doing when you put large number of links to each other, and anybody comes, you can put a link to them, they do become important. Okay, right? So, is this a problem? Of course it's a problem. Okay, because essentially you are saying that adversarial collusion between pages can change the notion of importance of pages. Okay? So by referring to each other, a cluster of pages can artificially boost their rank. Although, of course, the cluster has to be big enough to make an appreciable difference. It has to be a big enough cluster with respect to the size of the graph. Here, this cluster was 2/3 of the graph. That's why it made a huge difference. Okay, if you and your friend put links to each other, you still may be losers, because there are not enough of you. But if this entire class colludes, you have something going. Okay, but entire tempi colludes, you have real good stuff going. Okay, and so as I said, by referring to each other, you can increase the thing. So obviously, if you're a search engine, you would like for people to think that the ranking you came up